Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in.
Okay, so this first question is a bar magnet gets pulled by a string through a coil. The current is initially negative. Explain what happens as it is pulled through and how could we get a positive current initially. So maybe it's worth mentioning first why you would get a current in the first place. So it says initially we get a negative current. So this is electromagnetic induction. When you move a magnetic field coming from this bar magnet relative to a conductor, this coil of wire, then what you have is you have the conductor cutting the magnetic field lines. You'll get an induced potential difference, and if you have a complete circuit, you will get a current. Now, it's really important for me to just state those things because very often they can give you sort of wacky or maybe a bit confusing versions of these style of questions. But more often than not, they just want you to mention those things, and that gets you most of the marks. Okay, but anyway, that wasn't this question. This question was, what happens as we pull it through to the current that's in your coil? So the second thing that you need to know about this is, if you think about it, you know, once this coil does have a current running through it, a negative here, current running through it, well, that current itself has a magnetic field associated with it. Okay, and we know what that magnetic field should look like. This is the solenoid, so it looks like the magnetic field that you get inside a solenoid. And the thing is that that field that you get is set up in such a direction that it's trying to oppose this movement of the magnet coming through the coil. That's more of just a side note, but that is actually one of your spec points, to know that this current will be set up in a direction such that it has a magnetic field that tries to push that bar magnet back out of the coil. Okay, so you have to do some work to actually pull this magnet through the coil. Now, what's going to happen here is you're going to get a negative current, then it's going to go to zero, then eventually when it comes out the other side, it's going to go to a positive current. And how do I know that? Well, that's to do with the idea of the direction of current changing, depending on whether you are pushing this bar magnet in or pulling this bar magnet out. So you should know that it makes a difference whether you push the North Pole into a coil or pull the North Pole out of a coil as to the direction of the current. So my answer, it will go to zero, and then it will go positive as the magnet leaves because you're pushing the North Pole in and then pulling the North Pole out. How can I get a positive current initially? Swap the poles around, so push the South Pole in initially here. How can we make the size of the current larger? Why is it a current, not a potential difference? So to make this current larger, maybe you could pull it through faster, so a faster cutting of the field lines, or you could add more turns on the coil, not more coils, more turns on the coil, or a stronger magnetic field, not bigger, but stronger. And why do I have a current, not potential difference? Clearly, I have a complete circuit here, which is giving rise to a current. Okay, next one, this shows a student pulling a wire down through those magnetic poles and inducing a current. Explain what would be different if the student pulled it upwards twice as slowly. Okay, so if they're pulling it upwards instead of pulling it downwards, then they have changed the direction, so that will change the direction of the current as well. And what's slowly got to do with anything? Well, if they pull it slowly, they are cutting those field lines slower, so fewer field lines cut per second, and that will also give you a smaller current here. Okay, on to actual generators themselves. So it might be worth listening if you're combined, but you don't need to know the specifics of a DC generator versus an AC generator. Okay, what does a split ring commutator do in a DC generator, and explain where the maximum current is produced? So again, you really just learn some set phrases here. So your split ring commutator, just like in your DC motor, swaps the contacts every half turn, and what that does is it keeps the current in the same direction. Okay, good. Explain where the maximum current is produced. So you'll get the maximum current as this coil spins when it is in the horizontal position that's actually shown on the top right hand side here. So when I call this a horizontal position, but you might want to draw it to be clear. When it's in that position there, it is cutting the most field lines per second. So you get the maximum induced potential difference and you get the maximum current in that particular position. Okay, what do slip rings do, and when does the potential difference graph go below the x-axis on an AC generator? So slip rings are your AC generator's way of connecting this coil to the external circuit, and those keep the contacts the same every half turn, which therefore makes the current alternating. Okay, so it's a bit counterintuitive. The contact staying the same makes the current alternating, and in my DC one, the contacts changing every half turn makes my current direct. Okay, when does potential difference graph go below the x-axis? So let's have a look at the graph first. So you might get a graph of potential difference with time that looks like this, and this is the coil going through one whole rotation. So the answer to this is, well, I've put when I go from a vertical position for my coil to another vertical position, but let's have some pictures to show you what I actually mean. So it's these two positions here. So when the coil, I've called that the vertical position, but when it's in that position there on the first picture, and then as it's turned through 180 degrees and goes back to that picture. How do I know it's that picture there? Well, when the coil is in that particular position, just at that second, it's not going to be cutting any of your magnetic field lines. So that's why I get this X on the graph there. That's the point where it's 0. And then you get your negative potential difference until it goes back into that position again and it reaches 0 again. Okay, DC generator. So the graph below shows a graph of a DC, that should say generator. Draw a picture of the current induced when the generator, is spun faster. Okay, fine. So we get this pattern here for my DC generator. Remember, this is still a direct current. Just because it goes up and down, it's all above the x-axis. So it's getting bigger and smaller currents, bigger and smaller, and that depends on the position that your coil's in its rotation. So remember I was saying, when you're in that horizontal position, you're getting maximum current, maximum cutting field lines. And then when you're in that vertical position, you're not cutting any field lines and you get 0 current. But okay, what did the question actually ask me? It asked me to draw a picture of the current induced when it's spun faster. So I should know faster relative movement of conductor and magnetic field is going to give me a larger current. So I want the amplitude of this graph to be larger, but also I am going to complete more turns in the same amount of time. So I need my time period to also be shorter. So I'm looking for a bigger amplitude and a smaller time period, smaller space between these waves. Okay, and below shows a graph of an AC generator. Draw the graph if you swap the poles of the permanent magnet around. Identify one full turn on the graph. Okay, fine. So I've got this here, but if I were to swap the poles of the magnet around and do the same thing again, I would get in the opposite direction. I would get my, whatever this is, current or potential difference in the opposite direction. Okay, identify one full turn. Well, it's one complete wave, so from crest to crest, that is one full turn of my coil.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
my tips and tricks for this questions rather. Slip rings AC, split ring commutator DC. So they sound very similar. Remember which one is for which. Yeah, and it's confusing that you swap the contacts for direct current and keep them the same every half term for alternating current. So remember that as well. Size and direction of these potential differences in currents. Spinning it faster gives you a larger PD or large current. More turns on the coil will give you a larger PD or current, and a larger or bigger strength of your magnetic field as well. Final one, as I mentioned in the first slide of the video, there is a set response to whenever you have electromagnetic induction in your exam. Make sure you say fields moving relative to each other. Make sure you, not fields moving relative, conductor moving relative to field, or them moving relative to each other. The idea of cutting field lines, inducing potential difference, and then getting a current if you have a complete circuit.